Hey everyone, my name is Farjam Ashrafzadeh. It's spelled Farjam, so Farjam is totally fine if that's easier for you. So I'm a graduate from New Mexico State. I graduated in 2022 in industrial engineering for my master's, and I guess for some more context about me, I run my own personal drone business. It's called Aerial Amity LLC. I'm based out of El Paso, and my business started as a result of the pandemic, I guess, because I graduated with my undergrad from Embry-Riddle Aeronautical University in December 2019. Had all these beautiful jobs lined up. Pandemic hit in January, and everybody said, "Oh, furlough," and so I had to find a solution to make money. So I started my own drone business in 2020, and here I am 4 years later, still surviving, at least, right? Okay, so the other part of doing aerial surveys is that there's also RGB cameras that can be geo-referenced, right? So unlike Brandon, who deals with Lidar, my RGB photos basically can provide up-to-date imagery that is 100% geo-referenced down to 1 centimeters levels worth of accuracy. And that could be useful for your civil engineers, your architects, your Department of Transportation, anybody who's doing major changes into the land where they want to see how the land is changing over time, right? And so with that said, my drone deals with the real-time kinematics, the RTK. So as the drone is flying, it's documenting its position in three-dimensional space. It's documenting its velocity, and it's writing to every photo saying, hey, this image was taken at this time, and this next image is taken at that time. It does some inverse, and then finds out where that photo is relative to where the drone is flying and where the camera took that photo, right? And so let's see, what else? Because I'm dealing with RGB stuff, I have to be able to coordinate all the photos correctly. So I deal with these high-res, what are called ground control points. And basically, these are very high-vis targets that you can see from the drone camera. And that way, when you go back into the software and you start marking the photos for their geo-reference position, I can easily tell where some of the images were taken based off these ground control points, right? That makes sense. And so, yeah, so Brandon and I, we offer two different things, but principally we provide the same product. Both of our products can be overlaid with each other. So if you're dealing with like a company who's doing easements or they're running cables into some kind of land development that they're working on, we can throw Brandon's data on there and say, hey, we can find precise elevation for where everything's at, and then you overlay my RGB photos onto that, and then now we can all of a sudden see how that land is developing over time to make it easier for the construction crews or the civil engineers to say, hey, everything looks right, everything's going appropriately as planned. And yeah, other than that, I guess in terms of my drone, right, where'd I put her? She's over here. I'm dealing with your standard quote-unquote prosumer drones, right? So I'm flying the Mavic 3 Enterprise. And so what differentiates the Mavic 3 Enterprise from your standard Mavic 3 Classic or your Mavic 3 Cine is that the Mavic 3 Enterprise has the capability to attach an RTK module onto it. And so basically it's this little hat thing that's sitting on top. And this little device right here is communicating to my GPS receiver out in the field. And they're doing a bunch of different math that I can't explain. Your geomatics professor can't explain. I can't. And so anyway, so it's running all this math back together, and that's how it's basically, what's the word? Trilaterine where it is, right? Is that the right word? Would you try? Well, because triangulating is when you find the 3 points, right? Then trilateration is when you start converging things, right? I don't know. I just fly the drones. But anyway, and then some other differences. It has a built-in beacon on it, so that way you can communicate. That way you can broadcast a light out, inform any other aircraft that, hey, this drone is flying here. You can visually see it from the sky. And then it also has a wide-angle lens, so that way I can capture as much ground as possible. And then a telephoto lens in the case that I need to zoom into something that I can't really see. And yeah, any questions for me so far? That all makes sense, right? Okay, I see a lot of head nods. That means we're doing good. Okay, well, if there's no more questions, then yeah, Brandon, do you want to take it away with your demo? And then we'll do mine. Fly time. So, oh, it's fly time. Yeah, yeah, it's fly time. Yeah, mood. Okay, all right. Well, let's do it. Carry about 6 batteries on me. Six, yeah, I need 3 more. He looks into the data. He plugs all of it in. He starts coordinating with all the different photos and say, hey, this is this point on the face of the earth, right? They have the licensing. They have the accreditation. They have all of that. And so I do to the drone, and now it is flying that path on its own using the HereLink GPS module that we have on it. I have it doing a 30-meter spacing, flying 50 meters high. So I'm telling it right now to take Lidar data, and I'm also telling it to take a photo every 10 meters. It's going to go through and do all of that, pretty much like this whole canyon. The reason for that is we wanted to be able to show you guys like a really good change in elevation, a really good change in the terrain of the earth. If I just did it right over this, it would just look like a big flat plain, and that's not fun. All right, just finished its first leg, starting its second.
Can I ask questions?
Yeah, absolutely.
How big the wind this one can handle?
How much wind can it handle? So up to about 35 miles per hour wind it can handle. Right now we're at about 28 miles per hour, so we're still good. If the wind did pick up, then I would land the aircraft because it might not be safe. But like this thing has really big motors on it. It has really big propellers. It can keep itself stable in pretty high winds. Yeah.
Yeah. What's the time duration, flight time duration for this one?
Generally speaking, about 15 minutes per flight. Each flight, it operates off of 2 batteries. They're called lithium polymer or LiPos, 7,000 milliamp hour batteries. Both of them are put together into a series, so it has 14,000 milliamp hours. Gives it about 15 minutes of flight time. Sometimes more, sometimes less. It depends on the wind speeds. It depends on if I'm asking it to take photos or not. It depends on the spacing that I have it going. It also has terrain following features on it. So if I'm like going to be trying to do like that, like the mountain where your Aggie's A is at, it has known terrain data already stored in the drone, and it will keep within about 10 meters of that going up and down, so that way we can keep our spacing the way that we want it. So all these things contribute to battery life. I mean temperature even,
You get less battery like when it's cold?
So if it's too hot or too cold. If these LiPo batteries do not run well when they're cold, you have to warm them up before using them.
Yeah, that's what I have with my little DJI. It's cold.
Yeah.
Like it'll die immediately.
Yep. So a lot of people have heard of like lithium ion, but not a lot of people have heard of lithium polymer unless they're into like RC cars and stuff like that. The reason for the difference between them is that lithium ion can basically output like the same voltage like for the duration of its battery life, right? So from 0 to 100, it's putting out the same voltage, and then it just dies. Lithium polymer, it has a very, very high amperage output, but it's only good for a certain amount of time. So for example, this one, each battery has 6 cells in it. Each cell can hold 4.2 amps or 4.2 volts in it. After 3.8 volts, the battery's like not good anymore. So like there's really like a limited window of useful battery with LiPos because of the high output that they have. These batteries can be used to weld, to be honest with you. Like that's how powerful they are.
How did you map out its route?
Okay. So he just asked me, how did I map out its route? All right. I did it on this controller. I can also do it on my computer using a program called Q Ground Control. Essentially, what I did is I drew a polygon around the area that I wanted it to fly, and then I told it how I wanted it to be spaced, doing it in meters. So I told it I wanted it 30 meters spaced, and then I told it what angle I wanted it to be flying at, because I could have had it go this way, I could have had it go this way, or any combination of.
usually what I do is when I draw a rectangle, the longest part of the rectangle, that's the route that I have it fly because that's most efficient for the battery. If it has to constantly be turning, it's burning battery life. If it can just go straight, it's just a lot more economical. It's a lot better for the battery life. And that also feeds into your question of how long does the battery last. It's how efficient are you with the flight planning.
May I ask how much the drones cost roughly?
Absolutely. Oh, yeah, it's not a secret. All right. So Smart Drone is a drone manufacturer. We sell this drone. I'm also a pilot. I fly for civil engineers or land surveyors. I collect the data for them and deliver it to them. Or if they want to do it themselves, they can buy the drone. The price is not a secret. So it is $50,000 for that drone. And there's a lot of things that go into that pricing. A good bit of it is R&D. We had several engineers working on this for about a year before it was even ready to be on the market. We have pilots all over the place. The parts for the drone are not cheap, so like we have to make our margins. But yes, 50,000 is the price of the drone.
That include both Lidar and the camera and
Yes.
the toolset.
So if you do happen to buy this drone, you get the drone itself, you get the batteries, the controller, everything you need to fly it. But then you also get the software that goes with it. So it has processing software that is unique to Smart Drone. Like a lot of other companies, especially the ones that have Lidar, they also sell like a third-party subscription. Where are we at here? Should be coming back. Yeah. All right. So it's coming back. It's about to land. Um, yes, sir.
So related, if one of us was your customer today, and you did this scan, and you delivered a data set with the imagery and the LiDAR data, what would that cost the customer?
Okay, so that is dependent on acreage. So the acreage that I just flew right now, this would probably be about $1,000, maybe $1,500, give or take. But yeah, it's all something that is like, it's a case-by-case basis.
Of course.
They send us a KML or a KMZ.
Right.
I will bid on it and tell them this is what I can do the job for, and then they tell me yes or no. But yeah, on the low end, I've done a couple jobs for like $900. I have a bid in right now for a job that's $30,000, and that's 1,000 acres of very, very vegetated area in Colorado. So like, it costs a lot because it's hard work. Yep. Yes.
So you have to banging off the pine tree over there trying to check the repair the thing?
Well, Smart Drone will, yes. If I damage this, if anybody damages it, I will pick it up, put it in a box, I'll ship it back to Tyler, or I'll drive it back there myself, and then our engineers will do all of the repairs on it. So yes, when we sell the drone, it comes with a warranty, it comes with maintenance packages, things like that. The drone is like 100. Well, I can't say 100. Like the Chinese government having access to our data, and that was a problem with a lot of the drones that were coming out of there. Any data that flowed through them ended up in Chinese servers, and that was like it was an issue for national security. So we were really trying to go with an American-made or Allied-made product to kind of get around those things. Yep. All right, so the drone just did its autonomous flight, just landed itself. You just saw I was over here talking to you while it was doing its thing. Right now it is processing the data and saving it the way that it needs to be saved inside its onboard storage. Then it's going to save it to that little SD card. Once that's done, the drone's done. I can pack it up, put it away. I'll take that little SD card and I'll slap it on my laptop and I can start processing data. So you saw that. That was about a 10-minute flight to cover all of that area. I'll start processing it now while Farjam is going to do his flight. And the LiDAR data might be done before he's even done with this flight. It'll definitely be done before we get over to the classroom.
For context, since my drone is a little bit smaller, I have to be concerned with a few more different things than Brandon. So with his drone, he has big, huge propellers. He can worry about, maybe 30, 40 mile per hour winds. With my drone, it's very light. It's maybe 12 pounds. And why are you screaming? Take a gauge on how fast these winds are coming. Anybody want to take a guess how fast the winds are right now? 6 miles an hour. So almost there. So about 6 miles an hour per hour winds. Don't have to worry about that too much. So we should be fine and dandy and ready to go. When it comes to making sure the flight is going to run through correctly, I will normally in advance plan my area of operation, and I'll come take a walk right next to you real quick. I'll come by, I'll select an area that I want to fly. The drone will say, hey, okay, I'm going to fly that specific area, and I'm going to do it in this manner, right? And I can change that, I can specify it, I can change the overlap. Does anybody know what I mean by overlap? Any thoughts? Yes. So the spacing between where the images are going to take based on the flight path. So the thing about photogrammetry, right, so there's the flight path, you want to take a look at it. So the thing about photogrammetry is that we want enough photos to cover the entire area, but not too many photos to where it's going to jack up our processing time, right? Because imagine taking 4K photos, you know, we do about, I don't know, maybe 300 of that. That's maybe 9 gigs already right there. And so depending on who your client is, you really got to strategize on that. In terms of overlap, I typically do 70% front, 80% sides. So basically that means the drone is going to travel 30% forward, take a photo, right? And in that, so if you imagine my hand is one photo and this hand is another photo, right? If they're capturing the same thing, I want it to basically be like that. Right, so that way it's repeating that over and over and over again, finding unique points within these photographs, saying, hey, I saw this in this photo, I saw that in that photo, and it just starts merging the photos all together very well. The higher you go, the more photos you're going to take, the more unique points the software is going to find, and then the more complicated it's going to be to process. In terms of what kind of computer do you need, my graphics cards is a 3080, and then I have an i9 1100 something K or whatever. So I need a pretty substantial computer to be able to do all this, because the end result, you know, you're getting all these photos put together. That end result file can be massive. I had one where I did 165 acres. That file image was 22 gigs for that photo, dude. And so, crazy. But yeah, so anyway, so now I got the flight ready to go. I got everything planned. The only last thing with the ground control points that I showed you, I want to lay those out very spaciously, but also in an area where they can be seen from above, right? Because they're no benefit to me if a tree is covering them. And so I want to have them kind of evenly spaced out. I want to have one in the middle. I want to have one at a high elevation, one at a low elevation, so that way I can verify the differences in height and just make sure everything's functioning appropriately. And with that said, I believe we're ready to go. And away we go. Now some of you might ask, hey, how often do you get hit by a bird? It's happened twice in 7 years. And believe it or not, pigeons are the most likely to attack the drones, not the birds of prey. Which I thought was surprising. You would think a hawk would attack it, but no, pigeons. And so the drone is going to position itself. It's going to say, hey, I'm going to start from this point here, and there it goes. And so the whole time it's doing this, I'm validating on the screen, making sure everything's working appropriately, making sure the drone is flying in the way it should be, and keeping track of it. That's probably the hardest part about this, keeping track of where you're going, because once you start getting more and more acres, it gets a little crazy. So right now, I'm doing from that entrance of the road, going down to the end of the fence, down to here, and so that alone right there is 1.9 acres. And so if you want to take a look now, here I can see where the drone is flying. I can pull up the camera, make sure that the camera's working appropriately, make sure I'm able to see the GCPs and everything. And so imagine it's taking a photo, I guess what, one every second right now? So, yeah. And so believe it or not, in the span of 2 minutes, our entire flight is done, and we've captured the 2 acres. And so, yeah. And you can just see how stable it is up there. It's beautiful. I love the Mavic 3 Enterprise. And believe it or not, if you're familiar with DJI, the propellers on this one don't work with the Mavic 3 Classic, which I thought was interesting um, and rather surprising. Come on down. And you see, being connected to the RTK, it basically landed almost exactly where it took off from, which is kind of remarkable if you ask me. Um, and yeah, so that's pretty much it for me. Other than that, I think Brandon has his laptop out here. We'll be able to process it and merge it all together. But yeah, any questions, thoughts, concerns, curiosities?
If you don't mind asking, how much is it?
So the Mavic 3 Enterprise was 5,000, and then for the base station that was another 2,500, and then for the software that was another 500, another 5,000. So it's about 12,000 to get me operational. Yeah, but I mean, shoot, working with the surveyors, you can make good money back pretty quick. Yeah, yeah. Because surveyors, man, they make good money, dude. If they're doing like a standard meet and bounds for like a house, they can easily pull 3,000, you know? And so I come over and I'm like, hey, can you give me like, half of that or whatever? Man, no, that's too much. Maybe like 15%. But yeah, so I mean, it depends on your client, man. Because the bigger the client, the better. If you get contracts with those commercial guys, dude, where they're just completely destroying land for a shopping center, oh, dude, it's good money. Yeah, yeah, yeah. But the challenge of this is that uh, every photographer has a drone, right? So for me as a full-time commercial operator, um, I have to be able to convince these larger companies like, hey, I'm not just going to give you digital media. I'm going to give you a map. I'm going to give you a 3D model. I'm going to give you a topographic map. I'm going to give you, a digital surface terrain model, So it's the challenge for me, at least, has been going up against these photographers and, telling these big builders, construction companies, real estate people like, hey, dude, like, I'm giving you these pretty awesome stuff that can give you data. I'm not just selling you video and photo. But yeah, it's been a fun time. Um, but I like this industry because I get to work with everybody. So I work with Good Morning America, and so whenever they need drone footage, they call me. I fly out there. I work with AT&T and Verizon. If they ever need cell tower inspected, I go and I work with them. And I work with the Z-Tex Construction, Job Materials, and so I get to work with all these good people, and they treat me well, and it's nice because having my own drone business means I get to work for me. And I don't know if you guys are on TikTok and you saw that Mark Cuban talk where he said, oh, making 50,000 for me is much more worth it than making 100,000 for somebody else. I have to say it's true, man, because I could just take a vacation whenever I want. I could choose when to work. I can schedule things on my own. It's kind of a luxury. Yeah, doing this 5 days a month pays for my entire month, so I can't complain.
This is a smart drones processor. All right, this is something that's unique to our drone that can process the lidar data, like on the spot. All right. So what I'm going to be going through, some of these things should be looking familiar to you, I'm assuming. So I'm telling it what state plane we're in, New Mexico Central. I'm telling it what vertical datum I want it to be using, Joyd 18. And then I want what output units. And this depends on what the client wants. But so we traditionally use U.S. survey foot. Base station. So this is where I would take the Rhinex files out of the base station that I had, and I would implement them into this. I'm not going to do that just because it takes extra time, and we're on a very crunch timeline right now. So I'm going to do this thing called Infield processing, where it's still going to give us all of the data. It's just not going to be able to guarantee accuracy down to like the sub 2/10 of a foot. It'll be closer to within a meter of accuracy, and that's just the onboard GPS of the drone. It has nothing to do with the the PPK connection, or the PPK corrections. Yes, sir. Relatively accurate, yes.
What that means is that they don't be in the wrong position each other versus each other, the point of the X. But it's all with point up, shifting on good angle to the list.
Yeah, it's accurate relative to itself. Now also what I'll say is, so yeah, normally I'd be putting in information here and I'd be pulling in files here to improve accuracy, and then there's also a section for check shots. Now something else that I didn't do that I would normally do during a job is I would take that second GPS module that I had and I'd be going out taking measurements at various locations throughout the job site. And what this does is this ensures accuracy from my eyes. I'll take that data and I would pull it into the cloud software that I have, and then I can actually spatially see the difference between the check shots that I took with the GPS module and the points that are given to me from the GPS or from the drone, and then I can rectify the difference between them to get better accuracy. All right.
So what that means is you get integrated on the open shots we did last week into the system to check if they're very good. We did have an open GPS last month. You can influence the point and see if they are consistent.
All right, so now it's going to start its process. Now this is going to take, yes ma'am. Okay, glad you asked. I will show you that pretty much as like once the data spits out. But lightly what that means is when I'm collecting all of the data and I have all of the points from the Lidar cloud, it can't differentiate the difference between vegetation, whether it's just foliage or if it's trees, bushes, anything like that, and the actual ground. It can't do that initially. But the vegetation processor will do, basically it'll create an algorithm of point density, and it'll say, okay, I have a massive amount of density in this location, but then up here it's like sparse points, and it's able to say, okay, these are sparse points up here because it's limbs on a branch, and it'll just filter all of that off, leaving only the ground points. Now this comes in handy for land surveyors in particular, because land surveyors are really only, generally speaking, depending on the type of job that they're doing, they're only concerned with what the ground looks like, right? So they don't need to know, or if I deliver them data that has all of the vegetation implemented into it, they might look at that and say, oh, these are the ground points, right? Because that's what they need. But they don't need that, so I get rid of all of that and I only deliver them what's literally on the ground. Does that make sense? All right. I'm sorry, I tend to ramble and I tend to like over-explain myself. So just if I'm saying stuff that you guys are like, yeah, of course, just cut me off there and I will not feel a certain way about it, I promise. Okay. Are there any other questions? Because this is going to take like a minute. So right now you can see right here we're on step 1. It's going to go step 2, step 3 within the next probably 5 minutes. And then another couple minutes after that it'll be done and I can show you the LiDAR data. But it is going to take a couple minutes, so we have some time to kill if you guys have questions or... Oh, sure. That's actually a great idea. Okay, so are you guys familiar with the Dinosaur tracks in El Paso? Well, actually, I guess it's New Mexico, but in Sunland Park? Nope. Okay, so in Sunland Park, there's this company called Insights that is funding a kind of like a dinosaur track archaeological dig. They found several footprints, and they're like slowly chipping away and finding all of these other footprints that I try to identify what kind of dinosaurs were in the area. I went over there and I scanned it with my LiDAR, so I can show you that. It's not like super fantastic, but it is kind of cool. So our dinosaur tracks. I'm going to see if I can pull out a better photo, or actually just pull up the actual point cloud. All right, so this program that I'm using right now is called Cloud Compare. This is how I can actually visually see all of the LiDAR points that are obtained through the drone. So like this one right here, it was 1.5 million points, which is nothing compared to what I normally get. Like the one that we're processing right now will probably be about 20 million points. All right. So again, right now, nothing crazy to look at, right? But I can manipulate the data to be able to see it better. Okay. So I will do, it's called a scalar field, which basically just, it takes the z value, which, do you guys know what the z value is? All right. So it takes the z value and it assigns it a color based off of that. So the higher the number, it'll be red. The lower the number, it'll be blue. And it's relative to what's on the screen right now. So I will pull that up, export using z, and now you can start to see the curvature, right? And here, I'll zoom in. Like you can see the bushes. You can see the individual indents. You can see the cliffs. You can see the prints. It's all pretty cool, I think. So there are, when you're dealing with LiDAR data, there are some things called noise that you have to deal with. And just because of the nature of LiDAR, sometimes you get a couple of false points that are just like spots that are in like the middle of the air. So for example, I don't know if you guys can see this on your screen, but I'll zoom in. So these points here that are just kind of floating up in the sky, you might not be able to see them very well, but that happens for a main reason of there being particles in the air. So if there's dust in the air, it might hit those. If there's bugs flying, it might hit those. If there's birds, so like every now and then, like you'll have stuff that's just floating in the air. So you have to eliminate that. Yes. Yes, absolutely. So has anybody heard of Pix4D? Okay, so Pix4D is a software that really deals with data. Like that's just like its whole thing is dealing with data. One of them is Pix4D Surveyor, which is a program where I can put that LiDAR data in, and then there's just a little button that's like delete outliers, and it'll find those little specks that are off by themselves that don't have anything near them, and it'll just get rid of them, high and low. All right, I think our processor should be. Yes, so I can, here, I'll give you an example. What's going on here? All right, so it should be about done. I should be able to pull up our data very soon. So for example, I have this. I could, if I had, I don't have the photo of this right now. This is the Dinosaur version. But yeah, if I had the photo, I could layer the photo on it and colorize the point cloud to look like a photo, and then it's like a 3D model. And it's kind of like reverse engineering what Farjam does. Farjam, he takes the picture and can turn it into a point cloud. I can take the point cloud and turn it into a picture, kind of thing. It's taken some time. I apologize for this. I know it's as boring, guys. Just sitting there waiting for a bar to fill. Here's some other examples while we're doing that. All right, so like this is an example of like a finished product kind of thing. So after I take the LiDAR data and I can import it into CAD software, it'll pull up into here and create a surface, and we can then do line work with that. So I'll show you guys that. All right, so this is LiDAR data that was turned into, oh, come on. So if you can see all of like the white squiggly lines, I'll zoom in further. All right, so here we have contours that were derived from the LiDAR data. We have the photogrammetry that was done separately, that was layered on top of it, and then we're able to use the coordinates of this stuff on here and create line work. Line work is like when you're trying to mark anything that's on the photo or that's on the area. So if you have curbs, if you have manholes, trees, parking stripes, crosswalks, anything like that, it's stuff that would be marked and then like geo-referenced, and then you can take that and deliver that to a client so they know exactly what's on their property and where. So it's very software heavy, I will say that. All right, so now that it's processed, you guys saw how long that took to process that data. It's about the same amount of time every time to do the LiDAR data. Processing photogrammetry takes longer, but we don't have the time at the moment. So now that it's done, it put a finished folder in the folder of origin. I have my full processed result, which is every bit of data that it's pulled. So that's 17 million points. All right, so when you first pull it out, it looks like a big black blob because it's an intensity view. It got about the same amount of intensity, that means like point density, all across, so it all looks about the same. But if I had like reflective markers out there, or if there were parking stripes, they would blow up on this view right now. Like they would be bright white. You'd be able to see them very clearly. But I will take them and I'll put this back into a scalar field like I did last time. And now I have to get rid of that noise that I was talking about. So you see all of these random points that are up top. So I'll go like this. I'll look at it like this. Dust particles, variances in elevation, like it's called noise. It's very common in LiDAR technology. All right, so you can already start to see some contouring going on here, right? So this is like you saw the area that we flew. So you have your big. Oh, yes, absolutely. Like yeah, doing this much data by hand would just be an astronomical amount of time. Yes, sir. Oh, look at you guys. I'm out of school. All right. All right, cool. All right, so as you can see, like pretty much the backstop that we had was this giant, I don't even know what you call that, mound, right? So let's zoom in on it. Why is this not working? All right, so I would take this, and then I can take the 1 foot that has gone through that vegetation filter that you were asking about, and I can layer them on top of each other, and then we can look at the difference here. All right, so this is the 1 foot, or I'm sorry, this is the every bit of data that we have view. And this is 1 foot ground grid, all right? So we were able to see, oh, we got some weirdness going on here, huh? Now it takes off some more than what we want it to, which is fine. I can always go back in and add the data later. But you see how like there's all these holes and everything? Now there's reasons for that potentially. One, the reasoning could be there might be standing water. LiDAR data does not take water because it's reflective and refractive. Light beams hit it and it bounces away, doesn't make it back. So those usually show up as holes. We ran it through the terrain filter. So with the terrain filter being there, or the vegetation filter, I'm sorry, that will say, okay, I have this massive amount of points that are above the ground that don't look like they should be there, and it might cut it off. If it cuts it off too low, it might eat into ground, leaving empty holes like that. So I can always go back in and fill them back in with the data that was taken out, and that's not a problem. I just need to be able to verify that that is, in fact, at the right level. And then, honestly, that's kind of it for the 1 foot. Because like I would take it, I would clean it up, make it look all pretty, and then I would convert it into like a .text file or a .xyz file, and then I can send it into the CAD software and create the surface and deliver that to the land surveyor. All right. So does anybody have any questions about like what this looks like, or like what the process is, or how it's used? No? Okay. Did you say something? Oh, I just asked if anybody had any questions. For like CAD software, or the process of doing this, pros, cons, anything like that? Sure. So the goal of mapping the dinosaur tracks? So honestly, it was really for the archaeologists and that are over there working. They just wanted to see if there was a way that they could look at it and visualize it and maybe be able to make a 3D model out of the footprints and everything. So actually, at the end of this month, there's going to be an event over there that they're inviting everybody to, where they're going to have a terrestrial LiDAR, which that just means a LiDAR sensor that is on the ground, not in the drone. And they're going to try to get much closer scans of those footprints and see what they can pull up, and like have like a little barbecue and stuff like that. So if you guys are interested in the dinosaur tracks, feel free to head out there. 26th. Okay, I thought it was my bad. I said 27th, I think. Awesome. Okay. So that's really all I have to show you guys. Like, this is just kind of the process that I go through, and and then I showed you, like with the CAD software, like how I can deliver it to the land surveyor, and like the value that they get out of it is that, yes, yeah. If he wants to know the depth of it, like there are ways of getting that, but LiDAR probably is not the answer, because like, yeah, you would have to wait until it's dried out to be able to get the exact depth. But there is this thing called bathymetrics, where they use like a variance of LiDAR, and then they also use a little bit of like sonogram technology to be able to pierce through the water to be able to map out the terrain of the bottom. That is good for certain things, but like at a certain point that doesn't work well either. But yeah, if they really wanted to know what was in their lake, they would have to use something other than LiDAR. It's the way it is. What I would probably recommend is trying to do it manually, or waiting until it dries out. All right. So I'll show you an example real quick of what it looks like when you fly it over water. right, so this is called a TIFF, which is those stitched together photos. All right, so this was flown. This is a 50-acre flight. Lot of data. But as you can see, this is all water in this section. All right. So if you're not familiar with the area, this is Keystone Heritage Park, which is like right down the road from. It's in Southern Park. I can't remember what road. It's off of Donovan or something like that. But yeah, so it's a large park that they're trying to keep the area reserved for wildlife and everything like that. So they asked me to fly this, or Dean asked me to fly this. He is a surveyor that is in the area, and he was trying to do them a solid and get them involved in some stuff. So this is the TIFF. This is like 1,500 photographs all stitched together into one giant photograph. It is geo-referenced, like you can look at anywhere on this, and if you pick a point, it is accurate down to, you know, like this close of vertical and horizontal accuracy. Now, if I pull up the point cloud, all right, so you see that all that area here in the middle where it's all blank, because that's where the water is. Every now and then you'll get some, you might get a couple of returns. Usually you just want to kind of crop those out because you can't trust them. I think on this particular day there was a whole bunch of birds like bathing over here, and then as well as the water had receded a little bit, so there are some land bridges that you can see coming through. But yeah, for the most part, when you fly over water, this is the result, just a vacuum of data.
My part of the presentation, so I'm dealing with RGB photographs, and so basically, as I explained out in the field, the drone is going to be taking a photo at a specific interval. It can be 1 photo a second, 2 photos every second, or so on and so forth. But in principle, as each photo is taken, right, there's going to be attached an X coordinate, a Y coordinate, and a Z coordinate, right? And so that coordinate is going to change at every photo, in theory, right? Because the drone is moving in 3-dimensional space. And so as it's moving and documenting stuff on the ground, it's going to look for, the software is going to look for an object that is unique and repeatable in every photo. So let's say, for example, this triangle is somewhere out, some object out in the field, and the software catches it at this location right here. It's going to say, okay, I'm going to document this and say, hey, this triangular object is at this point, right? The next photo is going to say, hey, I saw that same object in this photo at this location, at this new X, Y, and Z. And then it's going to do the same thing over and over again for however many photos it's going to detect. In theory, if we're going to have 70% frontal overlap, that object would show up about 7 times within 10 photos, right? And so once the software starts compiling all these different images together, it's going to say, hey, I saw this photo was relatively around here. I saw this photo was relatively around here. It's eventually going to extrapolate that and interpret one larger photo that's going to have that object located at the fixed averaged location of where the software deemed it was compared to these averages that it observed. And then it's going to say, all right, that object's there in this location relative to the giant reference point of this entire photo. So this software is essentially doing that for every unique thing that it can find. It can be anything from a patch of grass to a building to the ground control points with the markers on it. And so it's going to do that hundreds to 100 to thousands amount of times. And the end goal is to make it ultra high resolution orthomosaic, so that way when we go and we project it for civil engineers, for surveyors, they can look at this map and say, oh, okay, we're working on this project here at this location, XYZ, here's my points, here's that manhole that's supposed to be installed, but the construction crew didn't do it. and so on and so forth. So basically, that's in essence how it's working. And each one of these unique objects, they're not necessarily the entire object. There may be a little shade of something. Maybe it said, hey, I saw this specific point at the other different photographs. And the way that it's going to derive that shape is that it's going to make a bunch of triangles. Anybody have an idea why we're using triangles? It's pretty comprehensive, pretty easy. It's because the triangle is the easiest shape that you can get in two-dimensional plane, right? Because that's the shape with the least amount of vertices and the smallest angles in between. And so ideally, it's going to look at a bunch of different points. It's going to say, hey, this point's here, this point's there, this point's there, this point's there. This point is here, and it's going to say, okay, these look all connected. Let's make a triangle here. Boom, bam, bam, bop. And all of a sudden, now you have a three-dimensional shape derived from a triangle relative to these points, right? And so that's where photogrammetry can be a very difficult topic to work with, because if you want to see something at a very, very, very precise level, you're going to have some averaging with these triangles. The software is going to do its best to make the triangles, but some of these triangles might be, a little offset. If it says, hey, I actually see a point over here, all of a sudden this triangle is a lot bigger than this triangle, right? And then this is the smallest triangle, and then you get some extrapolation error, and then it might not look very crisp. But once again, the more dense you have the software run, the more points you'll be able to find, and then in theory, the better shapes would come out of this. And this is where the you get what you pay for moment kind of happens, because with the software, I'm limited to how many points I can tell the software to derive, because it's looking at the photographs and deciding for itself how many points are out there. With Brandon's Lidar system, his is sending out millions of points, right? So his point cloud is going to be 10 times more dense than mine, and when you come to extrapolate his might be very sharp as compared to mine. So that's where it gets kind of difficult when it comes to pitching to these different companies, because you can say, hey, we'll give you this absolute down to the millimeter accuracy, or we can give you a visual approximation of what things look like. With me, the max that I can get is 1 centimeter's worth of accuracy. After that, that's when it gets a little too blurry, a little too distorted, and civil engineers and surveyors can't really use it. So in the case of maybe they're doing like a quarry, and they're allotted a specific amount of land from the city, they might use Brandon to say, hey, Brandon, we need to know the exact precise volume of everything that we're looking at. Versus with me, I might go in and say, oh, okay, I can give you what the quarry looks like right now, so that way they can identify any hazards, or say, hey, we need to change the planning for this because this land is falling over, and so on and so forth. But yeah, and then looking into the software, the first thing it's going to do is that it's going to look at every photo, and it's going to say, okay, where do we think this photo was taken, right? And it's going to say, all right, I see this photo was taken here. We had a slow start here, so it might have taken 2 photos right there. And then eventually, I had it set to a time interval, so it was taking 1 photo every, I think it was every second. And then so you can see right here where it's slowing down for the turn, it took a little bit more photos there. And then, so once these photos are inputted, they are then compared to the RTK data, and then the software is going to calibrate those images to say, hey, okay, let's see how tight these photos are relative to what the GPS is saying. And so right here you can see some difference, because this might be where the photo was taken, but this was right where the data was logged. And so that small little instance, in the micro sense, can be significant, but in the grand scheme of everything, I mean, it came out pretty solid, all intents and purposes. I also didn't do any corrections yet. I can use extra software, like Brandon was saying. There's a whole lot of software out there to make this more refined. I can do a comparison with the CORS network. Do you guys know what the CORS network is? I see one head shaking. So the CORS network, it's basically a bunch of GPS modules spread out through the United States, broadcasting GPS data for your phone, your cars, things like that. And so I can compare what the drone captured to that data, and I can refine it a little bit better. And so now, at this point, this is what's called a digital surface model. This is basically a model that's going to show elevation changes, and it's not to be confused with the LiDAR data. This is basically comparing the triangle meshes from the point cloud to say, okay, we think the elevation is going to be like this. So we know the canopy was right around here. Here's the satellite dishes. So this is reporting a higher elevation. And then we had that ditch that was over here, right? And then so we can see it kind of right here. And we can see that this is at a lower elevation. And then right here in 1%, we're going to have the ortho. So my flight path, as you can see, was pretty much all of this right here. And even though I only flew that path, because the drone was so high up, it was able to still capture a little bit more than what was necessary. And okay, so looks like our model is done. And now this was 78 photos in 2 minutes. And we can see it came out relatively good. I mean, check that out right there. Look how sharp that canopy came out. But then you can see this was a little far away from the flight path, so there was not a lot of overlap happening right here. So that's where you can get some of that distortion because the software is making assumptions of what is supposed to be there. And then if we're looking at the ground control points, I mean, that looks pretty solid. And mind you, we're zooming in 1,000%, so it's going to look a little blurry because ultimately the drone is at 150 feet up in the air, so it might have took the photo maybe like that. And so yeah, but you can see, even though that we're looking at a bunch of dirt, this software was able to comprehensively capture the entire ground almost beautifully, almost to every rock. And so once again, the more overlap we have, the more detailed the map would be. And yeah, and so at some points the software doesn't like reflected materials, just like Brandon's LiDAR stuff. And so the roof of my car is a little shiny, so it might have reflected the sun a little bit and just caused some distortion there. But I mean, like, even for people walking around and moving, I mean, you guys came out pretty good, or at least the shadows did, at least. And then so along with this software, it also produces a 3D model from those triangles, and then now all of a sudden we can see kind of what's around there. And in this view, you can kind of see where the points were derived. You can see that it might have saw some points up here because the canopy might have been flapping in the wind or whatnot. And so, I mean, considering that this was shot looking straight down, I mean, it came out decently well. And yeah, so that's pretty much it. That's what we do. That's what me and Brandon do in a nutshell. So we'll give this to the surveyors, civil engineers. They'll extrapolate. They'll put their line work on there. I brought some samples, actually, if you want to see them. So these were both looking at driveways and roadways that they wanted to expand. And the visual image that you see there was captured from the drone. Both of them, I think, were 300 photos apiece. But the black lines that you see on there, those are what the surveyors had drawn and put over my data. And I mean, shoot, they came out fairly accurate enough for them to pay me, at least, right? And so, yeah, that's principally, I think that's it, really. Any questions about photogrammetry and the RGB aspect? No? All makes sense? Of course.